They want to discover something which is very, very tiny, called the Higgs particle.
They are trying to battle the Big Bang.
You might think that we have dropped in on a physics conference, but this is something quite different. It's a gathering of many of the world's experts on management, who have noticed that the Large Hadron Collider and its experiments at CERN have much to tell us about innovation and management. They have taken one of the two large experiments there, called ATLAS, as their focus. Fundamental physics, as illustrated by the ATLAS experiment and the LHC at CERN, has an impact on society in many different areas, some perhaps quite unexpected. What drives this research is working at the limits of technology to create conditions that existed very shortly after the Big Bang.
The scale of everything you find there is absolutely stunning. The largest magnets ever made, the biggest deployment of superconducting technology, the most powerful network of computers, the lowest temperatures, the highest speeds. Interestingly, the Swiss grid of electricity alone cannot supply the electricity they need. So they actually get most of it from France, and I was told that you can detect some of those particle collisions in the network grid in Norway.
The Large Hadron Collider takes protons, the positively charged nuclei of hydrogen, and accelerates them around a 27-kilometer ring under the Geneva countryside. 4 experiments sit at strategic points around the ring. By sending another proton beam in the opposite direction, both near the speed of light, they can engineer collisions at the experiments to reveal the innermost secrets of matter. The ATLAS Detector is designed to pick up the debris from such collisions and identify the particles produced and their energies. It's an extraordinary achievement of engineering, with different sectors geared to picking up specific particles or measure their energies. The size of a 6-story building, it's like a spaceship of the mind, a giant vehicle of exploration with a modern-day mission to open up new worlds, akin to that of Columbus with his own world-changing discoveries. Behind this groundbreaking detector lay an organizational challenge of equal magnitude. Fresh approaches to management and human and technological resources were created, opening up new practices of value beyond particle physics. The driving force is to find new particles at the highest energies ever achieved on Earth. The Higgs particle, needed to explain mass in the so-called Standard Model, is expected to show up. And in conditions close to those immediately after the Big Bang, a new family of particles is being hunted, linked to extra dimensions of space, predicted by the complex theories of physics. These searches inspire all concerned and shape the unique organizational approach of the ATLAS experiment. The scale and complexity of ATLAS is reflected in its contributing researchers. Some 3,000 physicists from 38 countries currently participate, ensuring both a variety of approaches and a sharing of resources. But there are further cultural and economic factors.
The world has changed because, of course, thanks also to the communication tools, more and more people can access the scientific information, and it's really a wonderful adventure for us to do such an exciting physics with so many different people, and each of them bring different traditions, different ways of approaching the scientific life and experience, so it's really wonderful.
So how does the process of fundamental physics propel our society forward? How can a scientific instrument like ATLAS and particle physics have an impact on society? In essence, it is about generating new fundamental knowledge that may trigger a major paradigm shift, a changed view of the world.
I think if you go back to the impact of the Copernican revolution on human thought, you would say, actually, that new conception of what the Earth was and its position in the universe initiated the age of navigation.
A key issue is that particle physics is curiosity-driven research, operating at a fundamental level. Professor Jürgen Renn, a historian of physics in the Max Planck Institute in Berlin, believes that such research will always provide advances for society, independent of the historical setting.
Hegel called that the cunning of reason, that the instruments open up a larger space of potential applications, a horizon of possibilities that you couldn't foresee in your theories. And that, I think, is the fundamental driving force why the curiosity actually has a benefit, because you speak to the nature through those instruments, and those instruments translate the novelties, the undiscovered aspects of nature into human insights, and that's the fascinating aspect.
The fact that particle physics progresses in generational jumps in technology also opens up a raft of opportunities. Economists call the opportunities options. This provides an intellectual framework to assess the long-term impacts we may expect from the ATLAS experiment.
Particle physics creates options. Just as when you invest in something, you create possibilities for the future. Options thinking are developed for responding to conditions of uncertainty. And particle physics specializes in dealing with uncertainty. Options are not just things that you buy and sell in financial markets. They're now moving into industry. People start reasoning. Whenever they've got a very large investment, they start reasoning in terms of options. How much flexibility are we building into this investment? How many choices does it open up for the future? My sense is that that way of thinking could enormously benefit how we think of science and our investments in science.
In terms of the ATLAS experiment, we can pick out three sources of options. ATLAS as an instrument, the detector plus data handling or information technology, the fact that this is fundamental science, and the organizational system, ATLAS and CERN. One of the most powerful illustrations of the options created by particle physics comes in information technology. The World Wide Web, created at CERN over 2 decades ago to open up access to CERN experiments, was a result of the need to solve problems at the frontier of science. In ATLAS, a new generation of computing called the grid is being used to respond to the torrent of data produced by particle collisions within ATLAS.
The computing infrastructure of the LHC experiment is really a big challenge because every year, to give you an idea, every year we have to move around across the world something like 50 petabytes of data. We need to process and reprocess order of 1 billion of events. So it's really a very complex model. And what is also challenging is a bit the sociology of this data distribution, the fact that this data have to be sent around through a very complex and very detailed network to up to the smallest universities and groups all over the world.
At the London School of Economics, Will Venters is a computing expert who was drawn to particle physics by the particular challenges of this curiosity-driven research and its working environment. He sees the successful development of the grid for particle physics as offering important insights for other endeavours.
I see parallels between the types of approach that CERN are adopting and their potential benefit in areas. For instance, I'm involved in an evaluation of the UK electronic prescribing service, which is a similarly distributed group of organisations, GP practice, software developers, pharmacists, pharmacy suppliers, etc., and a new technology that's being introduced to support them. And you could see similar tensions and similar paradoxes within that case, and that by discussing those and by raising them up and talking about them, you could see the benefit of that to many organisations.
The applications of grid computing now extend into several other spheres, including finance, earth sciences and medicine. It now forms part of a wider concept, better known as cloud computing. The instruments of science also present an interesting bridge between science and society at large. Consisting of over 10 million functional elements, the ATLAS Detector is arguably one of the most advanced instruments ever made. It's a complex mixture of a gigantic microscope and a super-fast digital camera of the 21st century. This role offers an insight into a new way of approaching history and how the future may unfold.
Science cannot live without instruments, and instruments are just the tools by which we interact with our environment. And they are hence a reflection of both, of the world out there and of our intentions, of our culture, and so on. And in the process of science, those instruments are developed. So there is a kind of evolutionary process at work here, where the instruments are kind of the backbone of that. They are sort of the genetic material of this evolutionary process, because they provide us both with continuity, because they are part of a material culture that we process, that we pass on in that development from generation to generation, and yet they are enabling also to act in new ways.
The stimulus to industry in the 21st century of this relationship between fundamental physics and instruments is huge. Due to the gigantic size of the ATLAS detector, industry is intimately embedded within the global detector construction process.
Most of what we do before we get to the science is engineering. So the LHC is a classic example of 27 kilometres of cryogenics, vacuum systems and magnets. So building the LHC involved something like 7,000 companies were involved in that. I think something like 1,000 developed new products as a direct result of that. So really the benefits to industry are that we give them rather taxing things to do in large numbers with very exacting standards. And by that, they tend to enhance their technological capabilities. They open up new markets. They develop new products.
How do options created because this is fundamental physics show up? The cultural effect of the new physics itself could be far-reaching. The most immediate outcome from ATLAS is likely to be an understanding of how mass was created in the early moments of the universe. But other revolutions in thinking are emerging from the ATLAS experiment and particle physics. One of the most compelling impacts is on the rest of science.
I think that biology, and looking upon this from a biological perspective, has much to learn from the type of thinking in physics. In my view, we're beginning to fully appreciate how complicated living things are. Probably more complicated than we thought. They're very, very complex and difficult to understand. And I think that complexity is going to lead to more abstract thinking, which is much more the domain of physics, who have been, for the last 100 years or more, but thinking very much in an abstract sort of way. So I personally think the type of thinking that it goes on in physics will greatly inform our thinking in biology.
So it's maybe difficult for me to switch to something.
This isn't just a vision. A team of biologists interested in the origin of life have seen how an experiment such as ATLAS and the organizational expertise of ATLAS and CERN can help their research. They visited CERN to discuss a potential collaboration, identifying several fruitful avenues.
And there's something special going on in the ATLAS project that is of broad significance. Second, with computing power. And third, if CERN agrees, by lending something of the prestige of its name.
A workshop at CERN uncovered common interests that may lead to a major new research strategy to understand how the molecules of life formed on Earth. This development was not foreseen. It illustrates how fundamental research can have quite unexpected impacts within science itself, but also beyond.
Even if you study a very particular problem, a physical problem like the law of projectile motions, it has consequences and implications in a wide range of areas. From the practical to the theoretical, mathematical challenges may arise from it, to the worldview, to religion, to the understanding of the place of man in the world.
The way ATLAS is organized and its global reach reflect an innovative approach of great significance. With 38 countries involved in the ATLAS experiment, there is a significant impact in spreading expertise from CERN to all corners of the globe, as well as attracting new manpower to CERN. One country which joined ATLAS in 2005 is Argentina, where involvement in basic physics is seen as important to improving many areas of life there. The ATLAS team from La Plata University is led by Professor Maria Theresa Dova. Her team of about a dozen physicists and physics students work on what is called the trigger, whose job is to sift the data from collisions to pick out only those events which might reveal interesting physics.
Hello. Markus, Nordberg. Welcome. Nice to meet you.
Two members of the ATLAS management met the Argentinian science minister and Theresa Dova to discuss the ongoing collaboration. For the minister, the advantages fanned out over physics and engineering.
For us, it's like a window to show the potential of Argentina in terms of contributing to the world science. Argentina is known for the contribution in other aspects, as biology and medicine. They were the only Latin American country who had 3 Nobel Prize awardees. But in physics, we think that we have a potential to participate in this kind of collective endeavor that is probably the most challenging in science today.
The stimulus of the ATLAS pioneering work on the grid has led to widespread interest in grid technology in Argentina and to this accreditation center setting standards in learning.
We learned about grid technology when we started working in ATLAS. Now we have a joint research unit, and the idea or the goal of this unit is to push a national grid initiative, and certainly this is something that only happens here in Argentina because our participation in ATLAS.
Another bridge to society in ATLAS comes via the research students, whose fresh minds are part of the lifeblood of ATLAS. For young researchers, the sense of being part of a large collaboration with a profound purpose is a strong motivator.
If we want an answer to something, we have to have thousands of us from all around the world, and we have to work together. And, you know, you get to talk to a lot of different people and present your ideas all over the place. And that makes it especially interesting. At the end of the day, between us, we get an answer, you know, to something amazing, like an extra clue to how the universe works. So you feel like you're part of something really huge. And it's also really, really challenging because you have to, you know, find very clever ways to do things.
Our students who are involved in these multinational collaborations, they experience a variety of cultures. There are hundreds of nationalities involved at CERN. Many of these people then don't continue in physics. They go out and work for multinational companies, and the experience they've had in this melting pot of different nationalities and different experiences and different methodologies and the way different countries and different nationalities go around these things, I think, makes these people more employable. It makes them better scientists.
Its biggest research unit, ATLAS, which we are highlighting today, as I told, has more than 1,000 doctoral students. There's one publication produced by ATLAS folks, for instance, that has 3,000 co-authors. The first 20 pages are names. The actual article is shorter, about 15 pages.
I think what we're seeing is something slightly odd. Science has always been portrayed as a pursuit with heroes, heroic individuals pursuing knowledge at the frontier, very often in opposition to their colleagues. But what we're seeing here is the growth of this thing called a collaboration, where nearly 2/3 of the particle physics community are actually engaged in the Large Hadron Collider. 3,000 of these are engaged in ATLAS. So what used to be a process going on, a multipolar process, now is a process with one main show in town. Well, this is bound to affect the way that social relations are built, the way that your work gets evaluated. I think we're moving into a different type of science, and I think we have to be very aware of this as time goes on.
Because this is curiosity-driven research, combined with the need to design and construct complex scientific instruments of industrial scale, ATLAS has evolved a distinctive system of management to achieve its goals. This challenges many of the established principles of modern management, as was apparent at the Rome Strategic Management Society annual conference.
The other thing I've done, just to get an inkling into their culture, is I content analyze the interviews that I've done with Dr. Bertolucci, but also with other distinguished members or coordinators of the ATLAS experiments. They don't like to be called managers, or they are coordinators. They are there temporarily. It's by election. They come and they go. And the word that came out strongly, most strongly, was the word we.
The management of the ATLAS experiment is elected, and consists of a spokesperson, deputies and coordinators. There is a core management group at CERN, but the large majority of researchers are spread throughout 175 institutes around the world. The decision-making process is collegial and consensus-seeking, where the role of management is to steer it. What ATLAS has created is a new type of social system, linking a strong and shared motivation with the ever-pressing need to find innovative solutions. It is characterized by what Will Venters calls collective agility.
I think their approach to doing it is distinctive. I think a lot of other people are trying to be agile, and I think new forms of organisation and collaboration are emerging which have some of this. At its basic level, they have difficulty coordinating, difficulty collaborating, and they have to do something that's innovative and new. And they also face the usual challenges of developing something like that. Things change, technology fails, unspecified changes are needed for requirements. And the traditional approach to managing those things is often formalist, so controlling it, basically putting in management control and organising it that way. But the particle physicists didn't seem to do that. They seemed to exhibit something that was much more about agile practices. Now, agile development practices are kind of very much a vogue and interest for small collaborative teams. So 10, 20 people working together to develop a piece of software, for instance. But not on this scale.
It is the impact on humanity at large that will be the long-term marker for this fundamental research. For the downstream effects of any physics discoveries, we must wait to see how nature shows its hand. But we can already identify some of the pointers in other domains. The effect of the latest advances in IT through the grid may transform many areas of life which depend on large-scale data transfer. The technology used by ATLAS and other experiments will also produce gains to industry and medicine a decade or so hence, notably through the reduction in the dosage of X-rays needed for human diagnosis. The effect on today's students of science could also be far-reaching, in motivating a new generation in the joys and benefits of scientific learning. The wider public seems also to cherish the ideals and scale of what is seen as a shared human challenge.
The public do get attracted to certain sorts of projects, and one of them is high-energy physics. I mean, it's sort of almost romantic. And so what I like about that is that not all science can sort of get out there and excite the public. Cosmology excites the public, in actual fact. So does high-energy physics. And so when CERN reopened, I mean, there was a wonderful flurry of excitement around that. That was reflected in the whole of the world's media. So it definitely has a sort of flag-bearing role to play for much of the rest of science.
Looking ahead to an ever more scientific and complex world, ATLAS and CERN can also inspire new organizational models for the emerging challenges in research.
I think one of the great challenges of the future is knowing that certain problems cannot be solved without fundamental science and its liberty, is how to create such cosmopolitan sites for the challenges that do imply biases, economic, political interest, like the energy problem. I think, there's a good example because there is a lot of fundamental research needed in order to solve the problems of sustainable energy, and not just in the natural sciences, but also in the social sciences, in economy, because you have to implement, you have to scale up these inventions. But how to do it like CERN does it without getting, all the politicians, all the large industrial corporations on the back. And I find it one of the interesting challenges of our idea, how to replicate the CERN experience in other fields, as free as CERN is.